how many types of waves are there? There are two types of waves. One is your mechanical wave, another one is your non-mechanical wave. The particles of the medium is said to oscillate about their mean position and it is perpendicular to the direction of propagation. Such kind of a concept is called as your transverse wave. The vibrating particle indicates the state of vibration with respect to 0 or with respect to 90 degree or with respect to 180 degree. These are called as phase of the waves. Hello everyone, I am Brinda from Department of Physics, welcoming you all to chapter 15. Chapter name is Waves. In today's class, let us just check about the waves. Wave is a form of energy which helps us to receive things, so that we can't see waves but we can feel it. That is with respect to sound or with respect to visualizing, like how exactly the wave moves. So here, first of all, what is wave? Wave is called as a disturbance which is created for a steady state of any objects. So as you can see here, there are few examples. Water waves, you can see whenever there is a stagnant water or a static condition water and you just drop a pebble on it, what happens? There is a wave which is created. And remember, one most thing is, for a wave to travel, there has to be any necessary medium such as air, water, etc. So dropping pebbles to a silent water is a kind of a disturbance which is created to it. So there is a formation of a wave. And here you can see a ear to which the sound waves are traveling in this direction. So these sound waves, in order to travel from one place to another place, it has to have a medium. But in vacuum condition, you will not, even if you scream or shout or do anything, you can't hear anything because of the vacuum condition. Because of the particles, that is the medium which is present in air. The air acts as a medium for a sound to travel from one place to another place over here. So medium is one of the most important concept here. Next is, let us just check types of waves. How many types of waves are there? There are two types of waves. One is your mechanical wave, another one is your non-mechanical wave. So what is a mechanical wave? The wave which requires a medium to travel is called as mechanical wave. For example, we can consider sound, because sound cannot move without a medium, sound waves. So another thing is non-mechanical waves. So what are non-mechanical waves? The waves which do not require any material for propagation. Directly we can consider it as electromagnetic wave as an example, because the light waves can travel in vacuum as well. So the velocity of light in vacuum is said to be 3 into 10 to the power of 8 meter per second. So that is about your types of waves. Other waves with respect to its dimension, that is how does it spread. The waves are classified into three types. It is one-dimensional wave, two-dimensional wave and your three-dimensional wave. One-dimensional wave can be the waves in a stretched string. The waves which occurs in a stretched string, as well as two-dimensional waves, it can be the waves in the water. Your three-dimensional waves can be your sound waves. So this is about different types of wave with respect to how it spreads. But here, these are the mechanical and non-mechanical. It's with respect to whether it needs a medium or it doesn't require any medium. So further studying, we will just hold on with mechanical waves. So we are studying with respect to sound waves in your class 11. So sound waves require a medium, and that medium is air. So it is one of the most important component. Without the medium, the sound never reaches from one place to another place. Out of the mechanical wave is classified into two types with respect to how exactly it moves. So one is transverse wave and another one is longitudinal waves. So first of all, let us study what is your transverse wave. The particles of the medium is said to oscillate about their mean position and it is perpendicular to the direction of propagation. Such kind of a concept is called as your transverse wave. So you can just see whatever I have marked over here, and give a wave representation. So you have your x-axis, you have your y-axis. So the particles which are in the medium oscillates. Oscillates how? You can see x-axis is said to be your direction of propagation. When x-axis is your direction of propagation, the wave moves in such a way that it is 90 degree to your direction of propagation. This holds good, like 90 degree to the mean position. Direction of propagation is towards x-axis, and this is the mean position, that is the origin. This red line is the mean position. So it moves in this manner. So such kind of a wave is called as a transverse wave, whose particles moves 90 degree to the direction of propagation. All the lines are at 90 degree to the direction of propagation. Such kind of a wave is called as a transverse wave. And next we are just studying with respect to longitudinal waves. In case of longitudinal waves, as you can see here, a wave in which a particle of a medium oscillate about their mean position along the direction of propagation, which means this is the direction of propagation, and it is not oscillating perpendicularly but about their mean position, in the sense you have movement of the waves are in this manner, that is, it is parallelly to that of the mean position. You can see the particles here spread out and compress. Again spread out and compress. So spreading out and compressing, spreading out and compressing. This happens, this kind of oscillations to and fro movement happens, because of which finally it reaches our ears from the source. Okay. So that is how exactly it goes. A wave in which particles of the medium will oscillate about their mean position, that is, it is moving parallelly and not perpendicularly. Such kind of a propagation is seen in a wave which is known as longitudinal wave. So next, going on to, in order to know the basic components of a transverse wave now. We consider this transverse wave and let us just check the basic components, how exactly it is. So we have your x-axis in this direction of propagation. Let us just mark it in this manner for you to know better. And this can be your y-axis. Otherwise, it is just a sinusoidal wave. So now for this we have, say this is our origin. First of all, let us just start from here. What is amplitude? When a wave propagates in a medium, the maximum displacement of the particle which is here, it is displaced maximum. So this is called as your amplitude. You call it as A. Amplitude is nothing but the height of the wave. Next is wave period. That means the time during which one complete wave is set up in a medium. One complete wave in the sense one complete circle, 0 to 2 pi. So it is seen here, 0 here is here. Here it is pi. Here it is 2 pi, here it is 3 pi. So 0 to 2 pi is from here to here. So this is called as time period, capital T. Next we have wave frequency. The number of waves, again the number of waves set up in the medium in 1 second is called as wave frequency. Suppose this is 1 second time interval and number of waves, this is one wave, this is one wave, this is one wave. So there are 3 waves which is exactly covered up with 1 second. So that is called as wave frequency, which is given in terms of nu. And the phase. Phase is nothing but the vibrating particle indicates the state of vibration with respect to 0 or with respect to 90 degree or with respect to 180 degree. These are called as phase of the waves. So next, it is wavelength. Wavelength is nothing but the distance between two consecutive particles in the medium which is vibrating in the same phase. So this we know in transverse wave, this part is called as crest, that is the peak, and the valley is called as trough. So distance between, this is one crest, this is one crest. Distance between two consecutive crests is known as wavelength, and it is determined with respect to lambda, or distance between two consecutive trough also can be called as lambda, that is the wavelength. So that holds good with respect to wavelength and its notation is lambda. Next we are going on with wave velocity. It's the distance travelled by the wave in case of 1 second. Is such kind of a concept is called as wave velocity, which is given by v. So these are the basic components for which we have to know for the further applications. So now we have called as progressive wave. So what is a progressive wave? Name itself tells progress, movement, continuous moving. So progressive wave. So let us just see its characteristics. A disturbance which propagates continuously. See, I have told you progress means there is a continuous movement continuously in a medium in the same direction is called as with a constant amplitude is known as your progressive wave. Few of its characteristics are when a wave is propagated through a medium by repeated vibrations of the particles of the medium about their mean position, such kind of wave. Which one? Progressive wave. And they transfer energy in the direction of propagation. The wave propagates at constant velocity and that velocity is known as wave velocity, which is given in terms of v. All particles will vibrate in the same amplitude and it has got same frequency. So obviously it will be with respect to simple harmonic motion as we have discussed in case of your chapter oscillations. And different particles will vibrate in different phase. Different particles of the molecule will vibrate in different phase. So that is all about the characteristics of this progressive and much more. So Newton's formula for speed of sound in gas is what we will have to check. In order to check what exactly Newton have given with respect to sound in gas, we will have to know. So first of all, Newton considered isothermal process and started calculating the sound in gas. Isothermal process will have an equation of PV is equal to constant. So on differentiating this PV, where the temperature is constant over here, differentiating with respect to volume, we have got PV by V, D of PV by dV, which is equal to, we have P into dV by dV plus V into dP by dV is equal to 0. So here dV dV is 1. So P plus V into dP by dV is equal to 0. Take this towards the other side. So you have P is equal to V into dP divided by dV. So now you can rewrite this as P is equal to, since it is negative, dP divided by dV by, it is V. So this is of the form which gives you a bulk modulus concept, and this is studied in case of your mechanical properties of solid. Bulk modulus, you can see this expression there. So now we can write this as P can be equal to B, because this is of the form known as B, bulk modulus, which is called as B. Now, applying it to the velocity of sound in gas, V is equal to root of, with respect to bulk modulus, if we go B divided by rho, we have V is equal to root of P divided by rho. On calculating this velocity of the sound in gas, we just get our value to be somewhere in 200 and to some meter per second. So which is not accurate. The theoretical value is not accurate to the practical value, because the practical value turns out to be 332 meter per second. So there is too much of gap between these two values. That is why whatever Newton was calculating for the speed of sound in gas was held by Laplace, and he gave a correction. So that correction was called as Laplace correction, because there was much of the differences between theoretical value as well as the practical value. So what is that Laplace correction? Since Newton used isothermal process, Laplace used adiabatic process. So in case of adiabatic process, we used a concept called as PV gamma is equal to constant. So in this case, we just use, that is, the heat is not being exchanged from a system to the surrounding or from the surrounding to the system. So here what happened, we have to differentiate this concept and with respect to volume and write d of PV gamma divided by dV. So which can be written as P into dV gamma divided by dV plus V gamma into dP by dV is equal to 0. Differentiating this, we have P into dV gamma, in the sense we can just write gamma. We have V gamma minus 1. So plus V gamma into dP by dV is equal to 0. This is with respect to the formula here. So we have P gamma V gamma minus 1 is equal to minus V of gamma into dP by dV. So we can rewrite this as P gamma into dV is equal to minus V gamma, and divided by V gamma minus 1 comes to the numerator. So it becomes minus gamma plus 1 into dP. So this cancels. So we have P gamma into dV is equal to minus V into dP. So rewriting this equation, we will have P gamma is equal to minus dP divided by dV by V concept. So P gamma is equal to, the whole concept turns out to be your bulk modulus, so it turns out to be B. So you can rewrite velocity of sound and gas as B divided by rho is equal to nothing but root of P gamma divided by rho. When gamma adds up with along with the P, we will have certain value which will be nearly equal to 332 meter per second. So that kind of a derivation is called as your correction, that is Laplace correction, wherein he corrected this by using a process called as a adiabatic process. Next, we are going on to principle of superposition of waves. When does this superposition of the wave happen, of the sound waves? That is, when a medium is disturbed simultaneously, continuously, at the same time by number of waves, at every point and every instant, the resultant it is the algebraic sum of the displacement of the medium due to individual waves in the absence of others. So a medium can be disturbed simultaneously by a number of waves. Instantaneous displacement of the medium at every point, at every instant, can be told as the resultant of the algebraic sum of what? Sum of the displacement of the waves. Okay, displacement of the medium due to which? Individual waves, not the collective waves it is, or single wave, it is due to the individual waves superposing on each other at that single time or that instant of time is called as superposition of waves or principle of superposition of waves. Next, we are going on to reflection of waves. So let us just check. When a mechanical wave reaches a rigid boundary, it gets reflected back, and it follows something called as law of reflection, which we study in case of your optics. That is, the angle of incidence will be equal to angle of refraction. All these are said to be the law of reflection, and it obeys the same concept with respect to law of reflection whenever there is a rigid body in the surrounding. So now reflection of waves can be echo and reverberation. So difference is, echo is nothing but the sound which is heard after the reflection at a distant rigid boundary such as walls, buildings or cliffs after certain interval of time. In order to have this echo, you need at least a minimum distance of 17 meters for the sound to echo. So reverberation means it's persistent remaining of the sound after the source has stopped. Okay, the sound remains. Such kind of a concept is called as reverberation. With respect to these concepts, we have to study what is meant by a standing wave. This is contrary to the progressive wave. So the difference between progressive wave can be in a other way of a standing wave. So if you know the characteristics of the progressive wave, on contrary, you can give the characteristics of the standing wave as well. So the two progressive wave with the same length and same amplitude travels with the same speed through a medium in an opposite direction. It will superpose each other. So resultant wave pattern appears to be, as you can see there, since it is steady or stationary concept, the resultant will appear to be as if it is in a steady state. Such kind of a wave is called as stationary wave. So by this we have two conditions. One is notes, position at which the amplitude of vibration of the particle is 0. Another one is called as anti-node. So if you have this kind of a concept, so these red dots are called as nodes, and this pink as well as blue lines are called as anti-node concept. So here anti-node is this, and the one point where the two waves superpose is called as nodes. So at nodes, the vibration of the particle is 0, and at antinode it is maximum. Vibration of the particle is maximum. So loop, the waveform between two consecutive notes are called as loop. That is, if suppose from here to here, this is a loop. Again from here to here, this is a loop. This much is a loop. Between two consecutive notes, the gap is called as loop. Okay. So having these concepts, we will have to check the characteristics of the wave here. The waveform does not advance through a medium, so that it doesn't move. It seems to be as if it is steady. Flow of energy, there is no flow of energy here, but in case of progressive wave, there is transforming of energy. The amplitude of vibration from point to point gradually increases from 0 at nodes and maximum at antinodes, and particle lying between two nodes moves in the same direction at the same time. Next is modes of vibration of a air column in a closed pipe. So closed pipe means one end is open and other end is closed. So this point is called as antinode, and the length you can term it as L, and this where two particles or the two waves meet is called as nodes. So one complete, that is between two nodes, you have one antinode, and this complete segment is called as lambda by 2. The value of complete segment is lambda by 2. So here we have half segment. So for the first one, you have L is equal to half segment. So multiplying this segment is nothing but lambda by 2. Half, this is L, lambda 1 divided by 2, because it's the first component what we are checking this for the first diagram. So we have L is equal to lambda 1 divided by 4 we have. So lambda 1 turns out to be 4L. So we have frequency nu is equal to V by lambda. So lambda 1 V1, V is V itself, lambda 1 is nothing but 4 times the L. So we have frequency is equal to V divided by 4 times the L. This is the first frequency. It's a fundamental frequency in case of this open pipe. Next we are going on to the second one. For the second one we have in the same manner, L is equal to how many segments it has got? This is one segment and this is half segment. So it is 1.5. So 1.5 is nothing but your one segment plus 1 by 2 segment. So it is 3 by 2, and segment multiplication it is lambda by 2. So L it is equal to 3 lambda divided by 4, and the lambda is the second wavelength what we are checking. So you have lambda 2 will be equal to 4L divided by 3, or frequency, second frequency will be equal to V by 4L into 3V by 4L. So this can be your second set of equation in case of the frequency. And finally, the third one turns out to be L is equal to, you have got one segment, two segment and half segment, 2.5 segments. So it is 2 plus 1 by 2 gives you 5 by 2 lambda 3 divided by 2. So we have 5 lambda 3 divided by 4. So we have 4L times divided by 5. This is the value of lambda 3. When you substitute it to frequency, we have V divided by 4L times 5. So all the denominators are same, wherein your frequency turns out to be 1V, 3V, 5V. So the ratio of frequency nu1 is to nu2 is to nu3 is equal to 1 is to 3 is to 5 ratio, odd multiples it is. So this is the modes of vibration in case of air column in a closed pipe. It is a fundamental modes of vibration. This is fundamental mode. This is third harmonic as well as this is fifth harmonic condition it shows. Okay. So let us move to the next one, that is mode of vibration of an air column in an open pipe. This is same as that of the previous one. This is half plus this is half. So we have it as 1. So the length is L, and we have for the first case, we have half plus half, length is 1. 1 into lambda by 2, you have 2L is equal to lambda 1. Frequency becomes equal to V by 2L. So the second one is Length is equal to, we have 1 and 2 half of segments, so it is 2 segment into lambda by 2. 2 cancel, so you have lambda is equal to L, so it is frequency is equal to V by L. Multiply it by 2, you get 2V into L. And third one is L is equal to, we have 1, 2, 3 segments, 3 into lambda by 2, so lambda is equal to 2 and this is 3. So here we have lambda 1, lambda 2 and lambda 3 concepts, lambda 3, lambda 2 and this is lambda 1. So now we have frequency is nothing but V divided by 2 times L and you have 3 on the top. So you have 1, 2, 3, denominators lies to be the same. So frequency 1 is to 2 is to 3 is nothing but 3 concept itself. So this is the fundamental frequency of this vibration, modes of vibration in case of the open pipe. So next is beats. Beats is nothing but waxing and waning of the periodic rise and fall. So you can see rise and fall of the thing. No, when this is fused with this, we get a rise and fall in the wave motion. That is called as waxing and waning of the wave is called as the beats. So in today's class, we have studied about the chapter waves components. Let us all meet in our next upcoming session with the other chapter. Until then, have a good day. Thank you.